Welcome to the lecture series on digital electronics. In today's session, we are going to look about the introduction to Boolean algebra. So what is meant by Boolean algebra? Who invented Boolean algebra? The Boolean algebra was invented by George Boole in the year 1854. Boolean algebra is a branch of mathematics that deals with operations on logical values with binary variable. In the last session, we have discussed about the logical gates and the logical values. The Boolean variables are represented as binary numbers to represent the truths 0 and 1. 1 equals true and 0 represents false. Boolean algebra is used to analyze and simplify the digital circuits. Consider this example. For example, see, if it is a rainy day, or if it is a hot sunny day, this is all right. I'm taking the output as taking an umbrella. To take an umbrella, what are all the conditions which can be considered? If it is a rainy day, we can take umbrella, or if it is a very hot sunny day, then we can take an umbrella. For any one of the case, we can take an umbrella. And here I have connected another gate. That is, if this, for these conditions, I need not to take an umbrella if I am traveling by a car, right? If it is a rainy day and if I am traveling by a car, I do not need an umbrella. Similarly, if it is a sunny day and if I am traveling by car, then it is not necessary that I have to take an umbrella, right? So this is a practical real-time example, and so from this example we have framed an expression. Okay, that is a plus b, that is plus in the sense, what is an OR gate? If any one of the condition is true, we'll be getting the output. So if any one of the condition is there, if it is rainy or if it is hot sunny day, then we'll be getting the output, right? And this is and with C naught. Okay, so C naught in the sense, I do not need to take an umbrella if I am traveling by a car, right? So because of that, we are using a NOT gate here. So if you see, this is an expression. I'm taking this expression as an example to design this logic circuit. So for designing this logic expression, then we need an OR gate and an AND gate along with an inversion NOT gate. So this is a circuit which I have implemented for this equation, equation 1. Now let us expand this equation. Let us multiply the C dash inside this. So see, this is the equation which it looks, that is equation 2. And if I draw a logic circuit for equation 2, this is the logic circuit for equation 2. If you see here, both the equations are same. Both produces the same output y. But see, when I just expand, what happens is the number of logic gates differs. Isn't it? Yes, here I have only 1, 2 and 3 gates. Here I have 1, 2, 3 and 4 gates. This is the reason why we do need loss, right? So if I have an unexpanded form of Boolean expression, then the number of gates which I need to implement that particular Boolean expression or condition will be high. When the number of gates increases, then obviously the size of the device increases and the power dissipation also will increase. Because of this, I have to simplify this equation. In order to simplify the equation, we need Boolean laws. These are the commonly used laws: the identity law, the complement law, the idempotent law, dominant law, involution law, commutative law, associative law, distributive law, De Morgan's law, absorption law. These are this I have written it for the law of addition as well as for the law of multiplication. So these are the Boolean laws available. And this is duality theorem, right? The duality theorem, right, the same thing. When a particular x or y is being added with 0, what will be the output? Similarly, when it is being multiplied, or when an OR operation is done with 0 and 1, what will happen? When an AND operation is done with 0 and 1, what happens? Similarly, when it is being self added or negated self operation is done, what will be the output? So you can see the difference. This theorem is known as duality theorem. Then De Morgan's law. This is De Morgan's law. So when we take the um, uh, NOT operation of an AND gate, we'll be getting OR gate. When we take NOT operation of an OR gate, we'll get an AND gate. This is De Morgan's law. So this is the way how De Morgan's law has been proved. The left hand side, and this is one De Morgan's law, this is another. And if you see, the left hand side and the right hand side for specific inputs are the same. Yes. So the De Morgan's law has been proved here. What are the advantages of using Boolean laws? It uses less number of gates, it reduces the cost, reduces the size too, and also reduces the power dissipation. So when a Boolean equation is given, Boolean's equation is framed from the problem statement. Before implementing the Boolean expression, we need to simplify it so that to reduce the number of gates for implementation. So in order to reduce it or in order to simplify it, we need laws, Boolean laws. So now see here, this is an expression. And if we simplify, yes, here I have mentioned the different laws which could be used. So here actually we have simplified it. Right, C bar negated version will give you 0. So it's simplified, and now you see here, suppose if I am implementing this as such, I'll be using n number of gates. Here it's not like that, right? It is very much been simplified with the help of these laws. This is the reason why we use Boolean laws. This is another example, yes, where this expression is being simplified to this one. Very simple here. Here we'll be using 1, 2 and 3 gates. Here we can use only 1, 2 gates, one OR and one AND gate. So this is another example, right? After simplification, the gates has been reduced to greater extent. Here 1, 2, 3, 4, 5, 6 and 7 gates are required. Here we need only one gate. Instead of 7 gates, we can achieve the same result with the help of one gate when we simplify the expression using Boolean laws. This is the reason why we go for Boolean laws, right? So here I have given an expression and the simplified version of this. This is for your assessment. Can you guess what are all the laws which has been used in simplification of this expression? Thank you.